Okay, so as I said earlier, we're going to be reviewing Newton's laws. So let's begin. And I think, if I'm not mistaken, we're going to use clickers eventually. So that'll be fun. Okay, so a force. What is a force? Not the force, not like Luke Skywalker, the force. Although I'm still working on my Jedi training. Haven't quite graduated yet. It is a physical quantity that can affect the motion of an object, and it is a vector quantity. And what does that mean, or why is it a vector quantity? Because it has, go ahead, Connor. Connor's got it. It has magnitude and it has direction. Remember, committing crimes with both magnitude and direction. The orange jumpsuit. Next year, Halloween. Find me an orange jumpsuit. So, forces are a vector, or vectors. Now, Isaac Newton, the dude here, he was the first person to clearly describe the relationship between force, mass, and motion. He took a lot of Galileo's work and sort of, investigated, wrote some laws down, and did some experimenting. He and Galileo were sort of the bookends of the Renaissance in science, I guess you could say. He was knighted, Sir Isaac Newton. Yep. Newton's laws of motion not only apply on Earth, but are true throughout the universe, in an ominous sounding voice. And when they are true throughout the universe, we say that they are universal. If you are on the moon, Newton's laws hold true. You guys are writing everything down, aren't you? Paraphrasing, awesome. Are there places anywhere where Newton's laws are not true?
We don't know.
We don't believe so. We believe that they are true everywhere. That said, there are certain situations where Newton's laws do not apply. So places, yes, but situations, no. And I'm just going to leave it at that for now. We'll get to it. Okay? Okay, now, please, please, please don't be one of those people that writes every one of these down. These are not, I'm never going to ask you for this list. This is simply, and every year I get to the slide and I go, why did I not take that? These are lists of forces that you're going to encounter in problems. Okay, so all you need to be able to do is recognize, oh yeah, that's a force, right? So, we'll go through them quickly here. Buoyant force, produced by fluids and acts upward. Okay, if you jump in the water, right, there's a buoyant force that holds you up, kind of thing, right? If you're falling through the water, there's a buoyant force that holds up. Is there? It says produced by fluids. It doesn't say liquids. A fluid is also air. Any gas actually is a fluid. So is there a buoyant force in the air? Like think about dropping a balloon. Yes, there is. It's kind of like an air resistance kind of thing, right? So there is that upward sort of buoyancy that you're going to encounter in problems. Elastic force is another one, produced by stretching, compressing, or twisting an object. And I should go back to the other day there when we talked about fundamental forces, right? Those are sort of the building block ones. So all of these are created from those. And this is a good example, elastic force. Like if you take an elastic band and you stretch it, well, it's the electromagnetic force that's trying to hold it together, right? So it's sort of a extension, I guess you could say, of the electromagnetic force. It's produced by stretching, compressing, or twisting an object. So you're going to, again, encounter forces, elastic forces, in problems. Electrical force, produced by interaction between charged particles. It's why the socks come out of the dryer sticking together, right? Electrical force, because of charged particles. Friction force, produced when one surface moves over another. It acts in a direction resisting motion. Are we going to encounter friction in our problems? On a regular basis, over and over and over. Friction. Kind of rubs me the wrong way. Thank you. Still working on my comedy contract. Gravitational force, produced by the attraction of any two objects, acts downward on Earth, right? And correct me if I'm wrong, but did we not talk about gravity the other day? Yeah, we did, right? Okay. Yes, I'm attracted to the pencil sharpener, right? And yeah. Magnetic force produced by the interaction of at least one magnet and another object. Okay, so these are all, again, simply forces that you're going to encounter in everyday life and maybe throughout the problem. So just recognize that they're a force. That's all, really. No big deal. Okay, here's where we get more sort of into the big deals. Let's start with Newton's first law. And again, I'm going to sort of give you the overview today, and then each one we're going to look at a little bit more closely as we go through. So, Newton's first law. Usually if I say an object in motion, an object at rest, okay, so you know it, but do you truly know what it means? And it's not really worded. We had this discussion. This lesson was taught yesterday morning with my other class, so we had this discussion yesterday. And in fact, I'm actually a little bit upset, I guess. Maybe upset's a little bit too strong. Concerned that it's taught that way. Because an object in motion does not stay in motion. Allow me to demonstrate. Here, I've got a vacuum scale. It's in motion. It didn't stay in motion.
Stop.
How come? Newton said an object in motion stays in motion.
Friction.
There is another part. That's the part that doesn't get taught at usually that earlier age, right? And so here's an updated version of Newton's first law. Don't write it, just listen for a second. If there's no force acting on a body, it will continue in its state of rest, or it will continue moving along a straight line with uniform speed. So in other words, objects in motion stay in motion unless there's another force, which is almost always not gravity, friction. Okay, go ahead and write it if you want. I would prefer to say objects in motion stay in motion, or objects at rest stay at rest, unless there is some force. Now the problem is that there always is that force. So people, you can say it, but do you really get it? And I'm going to be tricking you over the next week and a half to see if you get it or not. This is known as the law of inertia. Things like to keep on doing what they're doing. People don't like change. A lot of people, right?
That's why I use a debit card.
Well said. Good one. I'll remember that. People don't like change unless it's at the store. Right? This is known as the law of inertia. Now, you've probably all heard of or seen the tablecloth trick, right?
Yeah.
Have you seen the Mythbusters version of it?
I've never seen it.
If only there was some YouTube video that I could show you.
Only if.
Okay, so for those of you listening at home, I'm really sorry that I spilled coffee all over myself doing that tablecloth trick. I'll have to practice that. Too bad those of you at home weren't here to see that, but you'll see it on video later. Hey, here's a question for you. Go get a clicker. So the question is this object moving? It's like a game show, right? You win a car if you get it right. Is this object moving? I need that earbud. Is the object moving? Now let me just explain the picture a little bit here. We've got 50 newtons of force pushing to the right, 50 newtons of force, I guess, pushing to the left. So the question is this object moving? And I've repeated myself a few times, hoping that that will be enough time for everyone to complete. And that's not true. I forgot. It's a Y or N. Is this object moving? And I know that nobody got it right.
Oh, who's the rebel?
Because the right answer is, it depends.
Maybe add a third answer.
The right answer is not even up there. It's a trick. The right answer is, it depends. How come? Because it says, if, Travis, here's the learn part, if there's no force acting on a body, it will continue in its state of rest, or it will continue moving along a straight line with uniform speed. If there's no force acting on it, is there a force acting on it? There's two balanced forces, that's right, and so we say that the net force is 0. So in other words, there is no force, so the object keeps on doing what it was doing. If it was at rest, it stays at rest. If it was in motion, it stays in motion.
Until.
Okay? So yes, I did trick you, but I'm forcing the point here. The answer is it depends on what? On what it was doing before. It depends on what it was doing before. Okay. Here's Newton's second law. Again, I'll be doing some explaining, some description, and then I'll throw a couple clicker questions at you, so pay close attention. Newton's second law isn't taught so much at the lower levels. It's usually just written as a formula, but it says that the effect of an applied force is to cause the body to accelerate in the direction of the force. If I push something, I'll go back to my mapping scale here. If I push it in that direction, guess which way it goes? That way. Woo! It took Newton to figure that out. The effect of an applied force is to cause the body to accelerate in the direction of the force. The force and the motion are in the same direction. Okay, now there's a second part to this, and it says the acceleration, right, is in direct proportion to the force and in inverse proportion to the mass of the body. So what does that mean? The acceleration is in direct proportion to the force and in inverse proportion to the mass of the body. So what I'm saying there is, the greater the force, the greater the acceleration. The greater the force, the greater the acceleration. The second part says in inverse proportion to the mass of the body. If the mass of the thing that I'm pushing is bigger, the acceleration is less. Inverse proportion. The bigger the mass, the slower it goes. Okay, now for those of you that are mathematically inclined, it looks like this. A funny looking weird thing, F over M. Funny looking weird thing is a proportionality symbol. And you draw it like this. Yeah, exactly. It's 3/4 of infinity. People always say it looks like a fish. Okay? It means proportional to. A, the acceleration is proportional to the force. The bigger the force, the bigger the acceleration. Inversely proportional to the mass. The bigger the mass, the smaller the acceleration. It's the proportionality symbol. Okay, it means that the acceleration is proportional to the force, and the acceleration is inversely proportional to the mass. Okay, here's clicker number 2. And I've answered this for you. In other words, the more force, the more the acceleration, the less the acceleration, the same amount of acceleration, or there's no relationship whatsoever. Again, the more force, the more the acceleration. Okay, what is it for acceleration? The more mass, when you add stuff, the bigger the object, the more the acceleration, the less the acceleration, the same amount of acceleration, or there's no relationship. Don't listen to your neighbor. Think it through. Make an answer. The same amount of force. Correct answer is less. When you put books on the scale, it doesn't go as far. Did I not just do that? The same amount of force. With the same amount of force, the bigger the object is, the less it goes. The less the acceleration. Okay, it's important, you guys. You got to know this. Okay. Do not write these down. Okay? just say, listen to me and say, okay, I get that, right? Makes sense. If a force is applied to a body at rest, the body will begin to move. Allow me to demonstrate. Bathroom scale at rest. I push it. Ooh, it moves. If a body is moving in a straight line and a force is applied in the direction of motion, the body will accelerate. If it's already moving and I give it another push, not quite quick enough, what does it do? Speeds up. This isn't rocket science. Oh, hang on, maybe it is. If a force is applied in a direction not in line with the motion, the acceleration will be in the direction of the force. Jason, can I bother you to come up here and be my lovely assistant?
Stop him on.
Shaden, everyone. I just want to communicate. I'm going to be standing right about here. It needs to get at least get to me. Did you see that?
Yeah.
I applied a force in a direction not in line with the motion. It was going this way, and I pushed it that way. So the acceleration is in the direction of the force, which is like towards the back of the room. Easy stuff, right? There's the lovely parting gift for you later. That's the pencil I picked up off the floor. Okay, now, going back to Newton's second law. If we rework it, because nobody likes a proportionality statement. People like equations, because you can predict and you can solve things, right? So we're going to take our A is proportional to F over M, and we're going to rearrange it to the equation that you're most familiar with, F equals ma. And we'll be doing problems with that. F is equal to mass times acceleration. And the F is measured in newtons, which is the unit n, although I'm told that the proper way to do that is a lowercase n, although you very rarely see that. North America, we tend to put capital N's. Mass must be in kilograms, and acceleration must be in meters per second squared. Or meters per second, exactly. F equals ma. That, my friends, is Newton's second law.
Does anybody like actually put like m/s/s?
It's, yeah, sometimes. I've seen it before. Now you might wonder where this unit newtons comes from. Did you know that Isaac Newton invented the Fig Newton cookie?
Did you know it's named after Massachusetts?
Jared. It's completely made up. What's it named it after?
It's named after a small town in Massachusetts.
Which, oddly enough, it has been in the news, that's the place where the Connecticut school shooting happened about 4 or 5 years ago. Newtown, Connecticut. I think it was several small children shot. Yes. Newton did not come up with the cookie. That's the name of the town, Newton. That's where they make the cookies. They make them there. It's like a type of cookie called the Dauphin. Now, if you combine the units for mass and acceleration, mass is kilograms. Mass is not m. Well, mass is in kilograms, and acceleration is in meters per second squared. And so if you take them together, mass times acceleration, kilograms times meters per second squared, this is defined as 1 Newton. 1 Newton is 1 kilogram meter per second squared. 1 kilogram times a meter per second squared. What a weird kind of unit. So that's why they bestowed the honor upon Newton and said, you know what, let's come up with a unit of force. It'll be a kilogram meter per second squared or equal to that, and we'll call it a Newton. Now, one of my bucket list things is to have a unit named after me. Yes, Bennett's. So the question is, force is measured in newtons. So what would you measure in Bennett's?
Little squares.
Oh yeah, that's a good idea. The little squares on the quarter section of a square centimeter. You would then say, I like that, Zach. I think we did that back then, didn't we? So 1 Bennett is equal to 4 squares, I guess, right? Or 1 square is equal to 1/4 Bennett's. Very good. All right. let's talk about the third law. Now, before we get into the law itself, let's just remind ourselves, what's a law again? What's a, I should have did this in my other class, but what's a scientific law? Is it a theory that's been proven? Don't make me come over there. It's something that predicts, it's something that we always see, it's a regularity, it's a pattern, something that we've observed over and over, and we can use it to predict other things. So, Newton's third law of motion says, when one body exerts a force on another, the second body exerts on the first a force of equal. Why do you think I've underlined it? And important, and people don't believe it. I know they can say it, equal and opposite, and then I ask them a question, they do not give me the equal number. I'm like, did you not just hear what I said? Equal? Equal. Equal and opposite. Equal. What does equal mean, Anna? The same. The same. When one body, this is the action-reaction. For every action there is a equal and opposite reaction. If I come over there and I give Adam a smack with 50 newtons of force, my hand's going to feel 50 newtons of force. Don't worry, I'm not going to do it. Not going to do it. Okay? Every action, equal and opposite reaction. Force. This happens everywhere, right? Jaden's got a binder sitting on the table. Jaden's binder weighs about 10 newtons. Gravity's pulling down, the book is pushing down with 10 newtons. The table pushes up, 10 newtons. Equal. Equal and opposite. Right? There's the book on the table. Equal. I don't know, Connor. What's the answer? 50 newtons. I'm just throwing you a bit of a twist. So what did people write? We got lots of 50s. Did anyone put minus 50? No, lots of people 9. Yeah, okay. Equal. What does equal mean? The same. 50 newtons down, 50 newtons up. Again, wouldn't you rather be tricked on this now when it doesn't count? 50 newtons. Equal. Equal. The table feels the downward push of your hand. What do you feel? Scared that the table has feelings. Let me just mark this for a second here.
Someone actually put that in your class? Yeah.
Really?
I think I found it on the internet.